Hello and welcome to 16.3, the acid-base strength and equilibrium law. So for this one, kiddos, put your thinking caps on. Not that it's really hard, it's just really different. Kind of fun and exciting stuff. Okay, so in your data booklet, we already took a look at pages 8 and 9, I believe, where it's talking about acids and their strength. And you'll notice that there's a Ka value. But notice that there's no Kb value. So we're going to use our Ka value to find our Kb value. But first, before anything, we're actually going to learn about what the heck a Ka value is and how acids and bases and their strength. So we're be looking at pH, pOH, the hydronium ion concentration, and the hydroxide ion concentration. We're going to be looking at all of that and bringing it all together and have a really good time together. This is going to be a long one. So my apologies in advance. All right, so the first 6 acids, as you know, in the table from the data booklet are strong acids because they all react quantitatively with water to form hydronium ions. No need for a ice table. If you have a pH, you just can go straight into finding the hydronium ion because the hydronium ion concentration because almost 100% of a strong acid is going to ionize into or react with water, depending on Arrhenius' theory or modified Arrhenius' theory, to figure out the hydronium ion concentration. If life were that easy and we stopped here, we'd be done. But we're not. So let's continue here. So most other acids, unfortunately, are weak in that they react with water to a much lesser extent. For example, hydrofluoric acid, right? As you can see with hydrofluoric acid, it is not a strong acid. It is going to react with water to form hydronium ions and the anion. However, it does that with a far lesser percent. So what we have to do is we have to but learn about a whole other way of how to answer these types of questions. So the acid ionization constant, or Ka, which is featured in your data booklet, indicates the extent to which an acid will react with water to form hydronium ions, right? So if you take a look at your table, you'll notice that if the percentage is high, like if it's a high Ka value, like 5.6 times 10 to the negative 2, then that is a stronger acid, even though it's considered weak, because it has a higher extent or a higher probability that the acid will react with water to form hydronium ions. However, just so we know, let's just wrap our head around what the heck it is. What is a Ka? How to figure it out? Is there a formula? Is there an expression? It's a ratio of the ionized form of the acid to the unionized form of the acid. So here we have our ionized form, and of course there's just the acid itself, the unionized form. And once we have the concentration of all these three, then we can figure out our Ka. Now, this are, as you can see, the products. And here's the reactant. And we don't include water in this case, right? So that's not part of our reactants. So this is kind of like Kc, but we call it Ka because we're looking at acids specifically. All right, kiddos? Okay, so let's take a look at a question. Calculating Ka from amount concentration. So these are the steps taken when we're calculating Ka and we are given amount concentrations. Okay, I think we could do this. The pH of a 1.00 mole per liter solution of acetic acid is carefully measured to be 2.38 at SATP. What is the value of Ka for acetic acid? So really importantly, we have to kind of break this down and see that we're given a pH. This is good because a pH has to do, when you're looking at pH, you're looking at the power of hydrogen or the amount of, it's a measurement of the amount of hydronium ions. And we're talking about acetic acid, which is a weak acid. So they go together. So we're good there, right? Okay, and we also know acetic acid is weak, so we know we're probably going to dive into an ice table, which is probably your favorite. And the only other thing you're given is the initial concentration of the acid, okay? So first step, well, before we even get to the first step, let's just get everybody ready for figuring this out, is you're going to write out your equation. So you have your acetic acid, we're showing that it's going to react with water. And when it reacts with water, it's going to form hydronium ion and your anion, okay? It's going to react, and we have a donating of a proton. So this is definitely your acid. Okay, so when we have that all figured out, then we can write our Ka expression. It's your products over your reactant, right? So here's my products over my reactant here, which is basically just your acid. So cool, let's get this all set up. So your first step to answering this question is basically change your pH to the concentration of the hydronium ion. And we can do that by taking, do you guys remember this from Chem 20? 10 to the power of negative pH. 10 to the power of negative 2.3 is going to give you a concentration of 0.0042 moles per liter. But that's only the concentration of the hydronium ion in this little guy. Okay? All right, so we're not done. Not even close. All right, so it's a 1-to-1 ratio. If you take a look, it's a 1-to-1 ratio. So we can say that for step number 2, well, we can just say that it's a 1-to-1 ratio, which means that if we go over here, see over here, we don't have to worry about molar ratios to figure it out because it's a 1-to-1-to-1 ratio. This is our initial concentration, which is great, and we also found the concentration using the formula 10 to the power of negative pH, and we found it to be 0.0042. Now, really quickly, just to recap a nice table, if this is the initial concentration, we don't know this and we don't know that, so we have to give it a 0. Because it's a 1-to-1 ratio, these numbers are the same, right? Which makes total sense. However, this number, oh, where is it? Okay, very important that because we're just taking it to 2 decimal places, it stays the same. So don't worry about that too much. And another thing here that we have to keep in mind is that, remember, these are positive values and these are negative values, but we don't have to incorporate that into our Ka. So once we have figured out using our ice table, okay, we just kind of plug in our numbers at equilibrium. So this expression here is only used with equilibrium values. So we have to go into here to use these values and place them into our expression, right? And that's going to give you an answer of 0.000, what is it, 0.000017. So regardless of the numerical size, Ka values are usually expressed in scientific notation. And we do that because they're going to be small. So it's really undeniable, like they're going to be small. So here's another example. A student measures the pH of a 0.25 moles per liter solution of carbonic acid to be 3.48. So very similar, pretty much exactly the same steps. Calculate the Ka for carbonic acid from this evidence. All right, so first thing we're going to do is we're going to write our equation. We're going to write our Ka expression, and we're going to plot it with our entities, our products over our reactant, not including water, right? And we're going to go ahead, step number 1, and change our pH of 3.48 into the hydronium ion concentration. And we get a hydronium ion concentration of 3.3 times 10 to the negative 4 moles per liter. That's because we did our lovely 10 to the power of negative pH. And we know that, again, this is a 1-to-1-to-1 ratio. So if the concentration of the hydronium ion is 3.3 times 10 to the negative 4 moles per liter, we know that the HCO3 minus is also 3.3 times 10 to the negative 4 liters, okay? So we can actually just kind of figure this out without using a ice table, because you kind of see that it's always going to be the same. You're always going to have an initial concentration, right? Here's our initial concentration. The initial concentration of the products is going to be 0 and 0. Once you find the hydronium ion concentration, and it's a 1-to-1-to-1 ratio, that becomes the same. So really all you're doing is you're subtracting these two. That's really all you're doing. And because it's so insignificant, because you're subtracting such a small amount, 0.00033 from 0.25, we can come to an agreement that it's 0.25 moles per liter. So no need for molar ratio. There's no need to actually write out this whole ice table once you get it. Like at first you're going to, maybe the first few times that you do some practice, yeah, go ahead, write out your ice table, but you'll notice you're getting the same things over and over and over again. So do we really need to do it? No, we can go straight into finding Ka. So Ka, you just write your concentrations at equilibrium and over the concentration of equilibrium of your actual acid. Okay, kiddos? And that's going to give you, again, a small number, which is what we're expecting. 0.000000044. But we always use our scientific notation skills to get us an answer of 4.4 times 10 to the negative 7. And that's the Ka for carbonic acid. All right, so let's take a look again, and now we're not even going to show you any ice tables, or maybe, you know, I think we're ready for this. The pH of a 0.400 moles per liter solution of sulfurous acid is measured to be 1.17, so we have the pH, great. Calculate the Ka for sulfurous acid from this evidence. So again, to repeat, write out your equation. Basically what you're doing is just reacting your acid with water to form hydronium ion and your anion, right? You have your Ka, which is your products, your ionized form of the acid over your acid itself, or the reactant. We know how to go 10 to the power of negative pH to change the pH to the concentration, right? And that's going to get you the hydronium ion concentration. And then we also know that the hydronium ion and the other entity here, it's a 1-to-1 ratio, so it applies to everything. And then, of course, what you do is you take your initial concentration, subtract your 0.068, which is going to give you a concentration of 0.332 moles per liter. There's that shortcut again. There's the ice table, but you don't need it. I think we're good without it, but I thought I'd just throw it out there for you. And then you just plot in your numbers and let your calculator do the work, and you get an answer of 1.4 times 10 to the negative 2. Okay, so let's do something a little trickier and really concentrate on this rule of 1,000. All right, funny thing is, this rule of 1,000 is always going to, I have it on good authority that even if you were writing the diploma, or if you are writing the diploma, which you're not, the rule of 1,000 always applies. So this isn't just only sometimes, it's pretty much every time you're given this type of question. Predict the hydronium ion concentration and the pH for 0.2 moles per liter aqueous solution of methanoic acid. Okay, it's a weak acid. Of course, why wouldn't it be weak, right? And it's kind of tricky because all you're given is the initial concentration. That's it, that's all. And you're asked to find the pH. You're not given the pH this time. So this is a really fancy shortcut rule. So let's just, I'm going to read it to you, and let's just kind of think about it and be prepared to use it. The value for x in the denominator can be omitted whenever the original concentration of the acid is at least 1,000 times the numerical value of the Ka. This will always be true. If it weren't true, okay, if it weren't true, then we'd have another situation on our hands, which we'll talk about in a couple of minutes. So step number 1, using your data booklet, look up the Ka value, right? So we're going to look up the Ka value for methanoic acid, or also known as formic acid, and we find this value to be 1.8 times 10 to the negative 4. So that's your Ka value. So that you can put in your formula right away. And also you can write out your expression and write out your ionized form of the acid over the acid itself. And then you're going to use X to represent the numerical value for the equilibrium amount concentration of the aqueous hydronium ions. So we don't know anything other than the Ka and the initial concentration, right? And we're going to use our friend, the variable X, to help us out. Okay, lots of X's. Do you see what's happening here? Because this is all you know. This is all you know. This is all you can fill out your ice table with. That's it. It's a 1-to-1 ratio to 1 ratio, so you don't have to worry about a coefficient. The coefficients are always 1. The only thing you have to kind of realize is that you're subtracting here, right? Because if this is your initial concentration, you have 0 and 0 for these initial concentrations. So that's a negative value, and these are positive values. So for equilibrium, kiddos, For equilibrium, it's 0.200 minus x. Okay? And then we have an x here and we have an x here. Right on. So really, what we have is this crazy thing. X times x over 0.200 minus x. So let's talk about what should be done, and what I'll show you is what you do. So in your data booklet, you're actually given the quadratic equation, the quadratic formula, and in theory, we should be using this, okay? And I can read this to you, and really, you're gonna ignore me. So you're never gonna have to be using the quadratic formula, but the textbooks likes to show you that you should be using the quadratic formula. But why do we do that when we can go straight to here, right? So here's that rule of 1,000. You have your Ka is equal to your x squared. That stays the same. But here, instead of going 0.200 minus x, you just put 0.200. Okay? Now we can solve for x, no problem. You isolate x, and then you just take the square root, and you get an answer, right? So hydronium ion concentration is equal to 6.0 times 10 to the negative 3 moles per liter. Now, in order to find the pH of that, remember it's your negative log. The negative log of the hydronium ion concentration, use your calculator for that, and you get a pH of 2.22. All right, good times, right? Let's try another one. Predict the hydronium ion concentration and the pH for a 0.500 moles per liter solution of hydrocyanic acid. Okay, all of a sudden, this is an easy question. This is what I love about chem. When you first look at something, it feels so ominous. And then when you actually work it out, it's like, oh, it's not a big deal. And then right now, you're just going to go to your shortcut. You're not even going to worry about thinking about using the quadratic equation. Don't even think about it. So what you're doing is when you have a question like this, go to your table and find your Ka for your, what is it, hydrocyanic acid, right? And then pretty much the assumption is correct. It's always going to be greater than 1,000. It just always will be. So we go ahead right to here. There's our Ka value right out of your textbook, or textbook lies. It's out of your data booklet. You have your products over your reactant. And we know that we're going to be using x's, kiddos. We know, and we're not using this thing. We know that this is going to be x squared in the numerator. But instead of 0.500 minus x, you know it's just going to be over 5, 0.500 moles per liter. Right? So then we just basically isolate for x squared and take the square root, and you get an answer of 4.75 for the pH. For the concentration, you get 1.8 times 10 to the negative 5, and remember you have to use your negative log to get your pH of 1.8 times 10 to the negative 5, which will give you a pH of 4.75. So all of a sudden it becomes an easy question, not a big deal, right? Thank goodness for shortcuts. If you want to take a pause here and just kind of recap what was going on, great. I'm going to continue because now we're going to talk about KB. KB is a little trickier, not much, just a wee bit. But like I said, you can pause now and then get caught up, or you can just stay with me. All right. Base strength and ionization constant, Kb. Okay, now we're talking about Kb. Before we're talking about Ka, now we're talking about Kb, which is going to look exactly the same, except for we're using that expression when we're dealing with bases. So all ionic hydroxides completely dissociate upon dissolving, so they are considered to be strong acids. So if a chemical formula has the hydroxide ion in it, like sodium hydroxide, barium hydroxide, ammonium hydroxide, they're considered to be strong bases. If they're considered to be strong bases, they're going to dissociate completely. So this is going to just basically be a forward reaction. So let's take a look at this example. Find the hydroxide ion concentration of a 0.064 moles per liter solution of barium hydroxide. Barium hydroxide is a strong base because of the hydroxide, right? So now you have to dissociate barium hydroxide into one barium ion. Now take a look at the subscript. 2 hydroxide ions, right? And this is gonna happen. See, it's a one-way arrow. It's gonna happen more than 99% of the time. So we say that it's quantitative. So if we have the concentration of barium hydroxide, if this concentration is 0.064 moles per liter, we just use our molar ratio, right, to figure out the hydroxide ion concentration. This is a 2-to-1 ratio, 2-to-1 ratio. So our hydroxide ion concentration is going to be 0.064 times 2. See how easy that is when you're dealing with strong acids or strong bases? Not a big deal, right? But if we're not using a strong acid or strong base, you can't do that, because this is only assuming that it's almost 100% I guess effective, right? So most other bases are weak, right? In that they react with water to a much lesser extent. Here's an example. Okay, the base ionization constant Kb indicates the extent to which a base will react with water to form hydroxide ions. So your Kb is equal to your products over your reactant of a base, of a dissociation reaction of a base, okay? Or not even dissociation reaction, a reaction of this and water reacting. So this time it's accepting a hydrogen in order to get hydroxide as one of your products, and then you have your other product. So here's your products over your reactant, and remember we don't include water. So that's your Kb expression. So let's take a look at a type of question. A student measures the pH of a 0.25 moles per liter solution of aqueous ammonia and finds it to be 11.32. Calculate the Kb for ammonia from this evidence. Show the establishment of the reaction equilibrium using an ice table. All right, so let's break this down. Things are a little tricky here. We have the pH. We're given the pH, which is 11.32. However, we're not dealing with an acid here, kiddos. Okay, we're dealing with a base. And we're also given the initial concentration of said base. This is a problem. We can't use pH with a base. We actually have to use pOH with the base. So I'm going to show you a couple of different ways of tackling that question, okay? All right, so here's one way. This is the Chem 30 way, and this is the Chem 20 way. So both are absolutely relevant. Both are, you can use both strategies interchangeably, whatever you're comfortable with. When you're talking about the Chem 30 way, we know that to find the hydronium ion concentration, we just go 10 to the power of negative pH, and that's our hydronium, our hydronium ion concentration, right? And then we use this little thing, Kw. Kw is equal to your hydronium ion concentration multiplied by your hydroxide ion concentration, right? And we know that if I manipulate this formula, the hydroxide ion concentration is equal to Kw over your hydronium concentration. Remember, this is your Kw, 1.0 times 10 to the negative 14. Take that over 4.8 times 10 to the negative 12, which is your hydronium ion concentration, and you get a concentration of 0.0021. Or if you want, you can do it this way, the Chem 20 way. Your pH is equal to 11.32. pH plus pOH, as you remember, is equal to 14. So in order to find the pOH, you take 14, subtract 11.32, and you get 2.68. Once you have 2.68, which is the pOH, I can now find the hydroxide ion concentration is equal to 10 to the power of negative pOH. 10 to the power of negative 2.68 is 0.0021 moles per liter. This is the same. You're essentially doing the same thing just with different strategies. Each is fine, whatever you're comfortable with. Anyways, at the end of the day, we found our hydroxide ion concentration, which is 0.0021 moles per liter. Okay, so now we plot everything in. We have our initial concentration. We have our 0.0021. In this case here, it's a 1 to 1 to 1 to 1 ratio. We're not including this, so we're not even going to worry about it. So this is the same throughout. This is going to be the same, right, because you're adding 0 to this. and then you're taking 0.250, subtract 0.0021, and you get 0.248. Take these numbers, put them into your Kb expression, reactants, or sorry, products over reactants, and you get a really fancy answer of 1.8 times 10 to the negative 5. Once your calculator does all the work. And remember, we have to change this to scientific notation. All right, kiddos? Good times. You know what's coming, right? We're going to do something fancy. Okay, the Ka-Kb relationship for conjugate acid, conjugate base pairs. You already know what those are. Consider the case of a general weak acid of the form HX, so hydrogen plus any other anion that is considered a weak acid, and its reaction with water. So we're going to take H with any other thing, well, not Cl, because that would be a strong acid, right? You get what I'm saying? It's going to be reacting with water, and it's going to form, you have to decide here, in this case here, who's doing the donating, who is doing the accepting, and then we see that this is your acid, this is your base, and then if things change only by one proton, right, these become like a pair. So if this is my base, there's my conjugate acid. If this is my acid, this is my conjugate base. So we know this to be true. This is nothing new. And this is also telling us that your Ka is equal, also you know that the Ka is equal to your products over your reactants of an ionized form of your acid over your reactant, which is going to be your acid. So for the conjugate base xy, x to the power of the negative power, we're going to look at x negative plus water is going to give you your NeHX plus your hydroxide. So your Kb is, again, your products over your reactant, right? Notice what happens when we multiply these two equilibrium expressions. Now, you definitely don't need to memorize this. I'm just giving you the background info. This is an FYI for you. Ka times Kb, right? When we take Ka and we multiply it by Kb, we know that this is our Ka expression. This is our Kb expression. What happens here, kiddos? What is being eliminated, right? So once that's eliminated, we have this cool thing, which is hydronium ion. Ka times Kb, you're just taking a look at the hydronium ion concentration multiplied by the hydroxide ion concentration. So what does this mean? This means that Ka times Kb is also equal to Kw. And we know from our previous podcast that Kw is equal to 1.0 times 10 to the negative 14. So this is something that we can use in a little bit. Calculating hydroxide ion concentration from Kb. Solid sodium benzoate forms a basic solution. Determine the Kb for the weak base present. Okay, our table only gives us Ka, not Kb. What do we do? What do we do? Well, I'll show you. Not a big deal. So first of all, this, we dissociate it. This is our metal. This is our spectator ion, right? Not a big deal. It's this guy that's going to react with water. So we're taking that right here. The benzoate ion reacts with the water, right? And you have to see what is accepting a proton, what's donating a proton. So then you're left with these products. This clearly is your base because it is accepting a proton. So then this is your conjugate acid. Oh, did I say acid? So now that you found your conjugate acid, we can use that to find our Ka. So there's our Ka for the conjugate acid from this base. I know, let it sink in. You know, you can always stop my podcast and kind of go, I'm going to rewind that a bit. What just happened? And that's totally fine. But because anytime a base and an acid, when they react, you're always going to have another base and another acid. We just call them conjugate acids, conjugate bases. So this conjugate acid here, I can find the Ka for. So what do we do once we do that? Using the Kw relationship for conjugate acid base pairs, now we can find our Kb. So Kb is equal to Kw over Ka. This isn't so bad. 1.0 times 10 to the negative 14 over 6.3 times 10 to the negative 5. And remember, this we found because we just looked it up in our data booklet, and it's the Ka for the conjugate acid of the base in question. And that happens, so now we happen to easily find the answer, which is 1.6 times 10 to the negative 10. Right on. That wasn't so bad. Okay, calculate Kb for the weak base aqueous ammonia, commonly used in commercial window cleaning solutions. Write the equation for the equilibrium. So here's our ammonia reacting with water, right, to form ammonium ion and your hydroxide ion. So let's take a look over here. This is our base because it's accepting a proton. This is our acid because it's donating a proton. And this becomes, guess what? It becomes our conjugate acid. And this then is our conjugate base. Make sense, kiddos? So what do? We find our Ka of our conjugate acid, which is ammonia, or ammonium, I should say, and it's 5.6 times 10 to the negative 10. Once we have that, we can find our Kb. Kb is equal to Kw over Ka. You don't ever forget something as awesome as Kw. 1.0 times 10 to the negative 14 over 5.6 times 10 to the negative 10. And you get 1.8 times 10 to the negative 5. Not too bad. There, we just found our Kb really quick. No need for an ice table. It's nice. Okay, let's jazz things up a little bit, shall we? Find the hydroxide ion amount, concentration, pOH, pH, and the percent reaction. And all you're given is one thing. You're just given one thing, 1.20 moles per liter. That's it. Oh my goodness. Well, guess what? The rule of 1,000 for an acid also applies to any base. So Kb, in this kind of situation where you're just given initial concentration, what you can do is you can use this just general formula. Kb is equal to your x squared, because we're going to be giving x's, the variable x, because all you're given is that, so there's going to be x's all over in your ice table, over the original concentration. Okay? Nice. So the compound is sodium hydrogen carbonate, NaHCO3. The weak base is obviously, because you're going to dissociate the sodium out of there, sodium out, because that's your spectator ion, and you're left with HCO3 negative. Okay, so once you react that with water, HCO3 negative, and you're going to react that with water. Oops, and this is aqueous, right? What's going to happen? It's going to accept a proton, and then you are going to get your products. And you know just by looking at this, right, that one of your products is right here. And that's your conjugate acid. You take that conjugate acid and you look it up and you find your Ka. Your Ka is 4.5 times 10 to the negative 7. Now all you have to do is find your Kb. All of a sudden it becomes an easy thing. Kb is equal to Kw over Ka. So here's our Kb. But we need to find so much more. So now what do? So you're going to write the equation for the reaction and the equilibrium expression for Kb, right? So Kb is equal to your products, which are your ionized or your ionized form of your base over your base, which is HC3O. Oh my gosh, HCO3 negative. So here's that one bit of information. This is it, guys. Remember? And this is 0, this is 0. We know we're going to subtract x by this, right? Because this is going to go down and this is going to go up. So then we're going to add your x's here. And you're left with this guy and these two guys. And that's where we get our x squared over your 1.2 times negative x. But remember the rule of 1,000. We don't have to do that. So all we have to do is just make it over the denominator, right? There we go. So now all we have to do is just go x squared over 1.2. And we also have our Kb, right? So x is equal to, you have to isolate for your x squared, and then you square root it. So your x is equal to 1.6 times 10 to the negative 4. And that is your hydroxide ion concentration. Now you use that concentration to find your pOH, right? So you just go negative log of the hydroxide ion concentration is going to give you your pOH. Use the pOH value to find the pH. Oh my gosh, I'm still talking and it's only one question. 14, subtract your pOH. 14 subtract 3.80, which is equal to 10.2. One more thing, right? There was one more thing we had to find. Now here's the thing, kiddos. Lots of work in terms of using up a lot of paper and your pencil, and your hand probably gets tired. But it's not difficult. It's really not. It's the same steps over and over and over again. Alrighty. So let's take a look at the last bit. Percent reaction is the percent ratio of the equilibrium concentration of produced hydroxide ions to the initial concentration of the hydrogen carbonate ions. So all you're doing is you're taking your concentration of the hydroxide, comparing it to your concentration of your base, and it's 1.6 times 10 to the negative 4 over 1.2. So look at that, 0.013%. So it barely ever happens, okay? All right, last thing I promise, the effect of amphiprotic entities. Remember, amphiprotic entities can act as an acid or a base. So to decide which one, we have to compare the Ka value versus the Kb value. Okay, so if Ka is larger than Kb, then it acts as an acid. If Ka value is smaller than Kb, then it acts as a base. Oh, let me just go back. Here's our question. Which reaction predominates when sodium hydrogen sulfate, or NaHSO3 solid, is dissolved in water to produce HSO3 minus solution? Will the solution be acidic or basic? Okay, now all we have to do is reference your Ka and Kb, compare them. Ka, pardon me, is 6.3 times 10 to the negative 8. Where did that come from? It just came from your data booklet. The conjugate acid is H2SO3 with a Ka of 1.4 times 10 to the negative 2. So for the HSO3 minus, right, we just take our Kb is equal to our Kw over Ka, and our Ka, in this case, is 1.4 times 10 to the negative 2, which is going to give us a value of 7.1 times 10 to the negative 3. So the Ka value, here's my Kb, and where is my Ka? My Ka value for HSO3 minus exceeds its calculated Kb value. So according to the Kw relation and the equilibrium law, an aqueous solution of this substance will be acidic. Okay? All right, and that's it. That's all you have to know. I know it's so much. This is the last part, and I'm going to, for your exam, because you're not going to get a Chapter 16 quiz, for your exam, I will be giving you a study checklist so that you concentrate on the things you need to know how to do. All right, kiddos? Okay, have a great day.